All right, should we start? Welcome everyone. Today it's a great pleasure to have Nati as a speaker, and he will tell us about symmetries and anomalies in the continuum and on the lattice.
Thank you. It's a pleasure to come back to IAS. And this is really a very strange project for many reasons, which is reflected here in the audience. It's on the interface of many distinct fields, which would not be viewed as distinct. We see representatives of them here in the audience. And I think I will say very little that is not known in one form or another by practitioners in the various fields. But I think it's fair to say that nobody put them together in this form. So in that sense, it will be new. And since the majority of you have field theory background, I will pitch it in from that perspective, but I'll try to connect also to people who spent most of their lives on the lattice. So as far as topics, there will be three almost distinct topics here. One is the notion that I will introduce of eminent symmetries. These symmetries are in between exact symmetries of the system and emergent or accidental symmetries. You will see that they are in between in a very precise sense that I will explain. The second part, I'll discuss lattice models with anomalous internal symmetry. There's a manifest internal symmetry on the lattice. Finite lattice, finite number of degrees of freedom, exhibiting various anomalies. Specifically, this would be the C=1 compact boson, as it's known in other circles as the XY model in 2 dimensions. And the third part, we kind of combine the elements of the first two. I discuss lattice models, which have an anomaly associated with lattice translation. And that anomaly will end up being identified as the celebrated Lieb-Schultz-Mattis anomaly, but it will be presented as an anomaly. I'll give a very precise definition of an anomaly. And this presentation of Lieb-Schultz-Mattis theorem will be like an anomaly. And we'll discuss the anomaly matching condition. And we will see that the anomaly matching condition for this kind of anomaly would be associated with an eminent symmetry. So now we have to start defining what I was talking about. And let's start with a system that has a global symmetry. And it could be a lattice or some UV completion of something or whatever symmetry. And in general, the symmetry in the UV and the symmetry in the IR are both groups, but these are typically different groups. And there is a map between the UV and the IR. Every symmetry operator in the UV is a symmetry operator, so it gives us a symmetry operator in the IR. But the map is a homomorphism, more mathematically, and it means that an obvious part is it has a kernel. There are UV symmetries that simply do not act in the IR. For example, there's another massive fermion that doesn't talk to anything, and the low energy person doesn't know that this massive fermion exists, but there's fermion number in the full theory. Much more interesting are symmetries that exist in the IR, but do not exist in the UV. And they're very common. The first class of them is known in high energy physics as accidental symmetries. And in condensed matter physics, they are known as emergent symmetries. And they arise because we write the most general low energy Lagrangian invariant under the UV symmetries. And then we realize that if we limit ourselves to renormalizable operators, we exclude irrelevant operators, then that theory has much larger symmetry. That's very common. An example in the standard model is B minus L symmetry. The stability of the proton, there's an approximate B symmetry, an approximate L symmetry, and an exact B minus L symmetry in the standard model of particle physics. That's not believed to be a symmetry of the full model at short distances, but it is a symmetry of the effective Lagrangian, including only relevant operators. Try to write a relevant operator that violates the symmetry, and there isn't one. Another common example is continuous translation in lattice models. We start with a lattice model. There's only lattice translation by a discrete amount. If we take the number of sides to infinity and we look at low energies, it looks like we have continuous symmetry. That's not an exact symmetry of the model, but any operator that would break it is irrelevant. Now, the low energy theory, if we are more careful, includes also irrelevant operators. And these irrelevant operators respect true symmetry of the model, namely GUV. So for example, if we look at the standard model, there is violation of base proton decay. We can add it to the standard model by adding an irrelevant operator that breaks barrier number. And same thing with neutrino masses. We can add irrelevant operators that give neutrino masses to the standard model. We mentioned 5 operators. And they're being measured experimentally. They are definitely there. So this story is well understood, and people have been studying it for decades. These symmetries, the UV symmetries are exact symmetries, whether they act or not. The emergent symmetries are approximate symmetries. We kind of got them as bonus. They are there, but there's an approximate notion. What I'm going to emphasize in this talk is that there's a new kind of new symmetries in the infrared that are not present in the UV, and we'll refer to them as eminent symmetries. I thank Tom Banks for this word is outside my vocabulary in English, so I thank Tom Banks for suggesting this word. So I'll first define them. It will be a little bit abstract, but then I'll give many examples. So unlike emergent symmetries, there can be relevant operators transforming under the eminent symmetry, but they are just not present in the effective Lagrangian. So this is not a symmetry of the UV theory. It's not there, but there can be relevant operators in the infrared, which are not present in the effective Lagrangian, even though they respect the UV symmetry. Even more so, they're typically irrelevant operators that violate that symmetry or that charge under the symmetry. Even they are not present in the low energy theory. So the low energy theory exhibits an exact symmetry, which is not there in the UV. That sounds crazy. How can there be a new symmetry at long distances, which is exact? It's not violated, but there are relevant operators that could have violated it, but they're not there. And there are irrelevant operators that violate it, and they are also not there. How can it be that these symmetries, how can it be that these operators are not present, even though it's not an exact symmetry of the UV? So before discussing them in detail, I want to give some examples of such eminent symmetries that people are familiar with, so that will know that I'm not talking about the empty set. The first examples is electrons near the Fermi surface. Look at the dispersion relation of free electrons, and we feel the Fermi surface. At the two ends, imagine we are in one special dimensions. There are fermions at the two ends of the Fermi surface, and they exhibit relativistic dispersion relations, and the number of left movers and the number of right movers is separately conserved, and that's an exact symmetry of the low energy theory. Another example of that, which is actually deeply connected to it, is the example of staggered lattice fermions given by Kogut and Susskind. That's in 1975. I tried to look if there's an earlier example where this thing was phrased in that sense. And what happens there is that there is a lattice translation by one site. That's an exact symmetry of the lattice, but it's not a Z2 symmetry, because if we go to 2 steps, perform lattice translation by 2 steps, that's still a symmetry of the lattice, but the symmetry is not Z2. This Z2 symmetry, this Z2 transformation becomes a Z2 symmetry at long distances, which is identified as a subgroup of the internal symmetry of the long distance theory. As a result, the low energy theory does not have any relevant or irrelevant operator. So there exist relevant or irrelevant operators violating the symmetry, but they are not present in the effective action. So this is kind of in between the exact symmetries of the model that exist in the UV and the emergent symmetries that are approximate and exist, or because of that reason, in the IR. And I'll say a lot more about that later as we give more examples. So what's an anomaly? There are many definitions of anomalies. I think it actually started in this institution, but in slightly different contexts, people use different definitions, and that causes a lot of confusion. The definition I will use here is that the global anomaly G This is a symmetry group. Global symmetry G is an Hooft anomaly if it cannot be coupled to classical background gauge field. That's the definition I will adopt. And I'll give a lot of examples of it. The fact that it is called an anomaly reflects the fact that it is confusing. Because if it had not been confusing, people would not have called it an anomaly. Anomaly is something that is confusing. And indeed, I found the literature quite confusing. So not all, but some textbooks tell you that anomalies are associated with fermions. When I went to school, anomalies were peculiarities of fermions, and later there were also various self-dual fields. Then I also learned that anomalies are associated with divergences. The system has divergences and they have to be regularized. And when we regularize them, we can't preserve all the symmetries and so forth. So we're not going to see any of these anomalies if we have a finite set and a finite number of degrees of freedom. The condensed matter people became aware of anomalies a little bit later, and they tell us that anomalies signal an inconsistency of the theory. The theory makes sense only on the boundary of a bulk with a symmetry protected topological phase. I'm not making it up. This was copied word by word from papers of senior people in the field. I will argue that all these three statements are incorrect. And we'll go to the first example, which will demonstrate already that all of these ideas are incorrect. So the simplest anomaly is a two-level system. When I went to school, it was called a two-level system. I guess today it's called a qubit. And the Hamiltonian is 0. And we can ask, what's the global symmetry of the system? And the global symmetry of the system is SO3, not U2, not SU2, but SO3. And the reason is that the symmetry is not the symmetry of the Hilbert space, but it's a symmetry that acts on the operator algebra. So the global symmetry is SO3, and the Hilbert space realizes it projectively because it is in an SU2 doublet. And that's not a new idea. I think I found several references in the early 30s. Wigner is one of them. That's the standard reference. So believe it or not, this is even before I was born. So this is an example of an anomaly. The Hilbert space is not in a representation of SO3. Therefore, we cannot couple the system to SO3 background field, so it fits our definition. And we learn to live with that in quantum mechanics, the Hilbert space can be in a projective representation. That's just a fact of life. And that's the simplest example, as far as I know, of an anomaly. And as you could see, there is no need for an infinite number of degrees of freedom. This has nothing to do with divergences. We have a finite dimensional Hilbert space exhibiting an anomaly. It has nothing to do with divergences. And there's clearly no need for a bulk. It really makes sense on its own without a bulk. But you could say that this is a little bit too trivial. So let's go up in dimension and have an example which is a little bit more interesting. So we'll discuss the 1 + 1 dimensional field theory, the compact boson. So we have a scalar field with a parameter R, and phi is circle valued. This is a textbook example of a conformal field theory. This is the most widely studied conformal field theory. And it has two global U1 symmetries. There are also a bunch of discrete symmetries that I'm not going to discuss. So there's a momentum symmetry, this one. This is the net current. And there's a winding number, also known as vorticity. So in condensed matter physics, this is called charge in vorticity, and this is called momentum symmetry and winding symmetry in the string theory, using the string theory terminology. So these are two conserved currents. One of them is conserved trivially, this one, and the other is conserved because of the equation of motion. And there are two symmetries of the 1 + 1 dimensional field theory. And Schwinger was the first to notice that even though the charges of these two symmetries commute, the currents do not. And the commutator of these two currents has a Schwinger term on the right-hand side. And I think that this is the first place where there's a sign that there's an anomaly in that system. In fact, Schwinger did not quite describe it in that language, talked about the time component of the current and the space component of the same current. But that's the same as the time component of the other current. So the currents do not commute, but the charges do commute, and we'll come back to that later. And one manifestation of this anomaly, which we will discuss in detail, is the defects of the symmetry carry non-quantized charges. So that's a manifestation of this anomaly, but this is beyond what Schwinger did. And this model exhibits T-duality. We exchange phi with the dual scale of phi tilde. It inverts R, and the momentum winding symmetries are swamped. If there are any questions, please interrupt me, either here or from the Zoom. Okay, so these are the two dual actions. Phi tilde are circle valued, and these two theories lead to the same answer. And as we vary the parameter R, we have a one parameter family of theories. And there are some special points here. All of them will be crucial later in the talk. So I put it here for completeness. In this normalization, R equals 2 is what's known as the BKT point, which we'll soon figure out in the talk. At R equals √2, this model is is the same as a Dirac fermion summed over its spin structures. At R equals 1, the theory has an SU2 symmetry. That's a self-dual point. This is T-duality that maps R to 1 over R. And it's described also by the SU2 level 1 WZW model. So I'm sure everybody in the audience knows about that. Now let's deform the model by adding a winding operator. So I'm writing using the phi tilde presentation, and I'm adding cosine of phi tilde to the action. That breaks the winding symmetry. So that's a good model to study. And what happens now is that we should check whether term lambda equals 0, and then check whether the operator cosine phi tilde is relevant or not. For large enough R, the dimension of cosine phi tilde is large. Cosine phi tilde is irrelevant, so it doesn't matter whether we add it or not. The long distance behavior doesn't change. For smaller values of R, cosine phi tilde is relevant, and therefore the model is gapped, and the infrared behavior is kind of trivial. I want to emphasize that in this range of parameters, the winding symmetry is violated in the UV, but at long distances, there is no relevant operator that violates it, and therefore we have it as an emergent symmetry. Remember that, because soon I will have it as an eminent symmetry to be compared with what we see here. So this is well understood. I think when I went to school, all that was already understood.
Does it matter what's the value of lambda?
As long as it's small enough, it doesn't matter. When it gets sufficiently large, you need to be more careful how you define the model, the continuum model. Thank you for the question. So the emergent symmetry is violated by irrelevant operators. Let's consider a variant of this system where we put a factor of 2 inside the cosine. So now we still have the momentum symmetry as before, but the winding symmetry is now explicitly broken to Z2 because we have a factor of 2 inside the cosine. So I copied the one parameter family. But now what happens, the question when we turn on lambda, we should check when does cosine 2 phi tilde become relevant? When is it irrelevant and when is it relevant? It turns out that the transition point is at R equals 1. In this range, cosine 2 phi tilde is irrelevant, and therefore the model is gapless. It doesn't matter that we added this perturbation. And the U1 winding number is an emergent symmetry. In here, cosine 2 phi tilde is a relevant perturbation, and therefore we have a BKT transition, except that it's at R equals 1 rather than at R equals 2. And the model is gapped, and the Z2 winding symmetry is spontaneously broken. In fact, we could have shown, well, we can just minimize the potential and see that the Z2 symmetry is spontaneously broken, but we could have done that more conceptually without minimizing the potential. Looking at the UV, there is a mixed anomaly between the Z2 winding symmetry and the U1 momentum symmetry. That mixed anomaly between the Z2 and the momentum symmetry should be realized in the IR, and therefore the Z2 symmetry is seen here because the Z2 symmetry is spontaneously broken. We'll soon see analogs of these statements. Is that clear? I haven't said anything until now, except the use of the word anomaly that was not understood in the early 70s. That's really old stuff. So the emergent U1W symmetry, U1 winding symmetry, is violated by irrelevant operators. So and irrelevant, it is an emergent symmetry. So now we're moving to the 80s. And I'm going to phrase something from the 80s in more modern term. And that is to add a chemical potential to the system. I'm taking exactly this system with the winding number one operator added to the action cosine phi tilde. And there's a U1 global symmetry. And if there's a global symmetry, we can add a chemical potential for it. So the charge of the system, this is the charge, is the interval of phi dot, can be expressed in terms of phi tilde as the interval of d by dx phi tilde. And the action is written here, the action of the system with the chemical potential. Is this clear, or could I explain that better? Okay, so this is the action with the chemical potential. So X is a circle, and we normalize the chemical potential here such that the total charge is near little q. So what does this system do? So we're going to follow the previous logic. We'll first turn off lambda, analyze the system, and then we'll turn on lambda and see what happens. So if we turn off lambda, well, first of all, I change variables. I change variables such as here I have only d by dx of some variable, d by dx of phi hat. Here it makes no difference, and the chemical potential appears only here. This transformation is known as a spectral flow transformation, but don't worry about that. So I just change variables on this Lagrangian, this action. And for lambda equals 0, it's the same problem as without the chemical potential. The fact that we have a chemical potential does not change the answer. The small fluctuations there are exactly the same as without the chemical potential. And again, that follows from something in conformal field theory known as spectral flow. But what happens if we turn on lambda? This operator might or might not be relevant. That depends on R. Depending on R, this operator is or is not relevant. But regardless of whether it's relevant or not, it oscillates rapidly as a function of X. So if Q is large enough, this operator oscillates very rapidly as a function of X, and therefore it does not contribute to correlation functions of low energy states. So any matrix element of low energy state with an insertion of this operator is 0, simply because it oscillates rapidly and the fluctuations, and it's washed out. So this is a new way of suppressing operators at long distances. And I claim that this model has an eminent U1 winding symmetry. It's not a symmetry of the short distance theory, and it emanates from the UV translation symmetry, hence the name. So the model has an interesting interplay between winding symmetry. So the momentum symmetry is exactly as before, but there's an interesting interplay between the UV translation, IR translation, and winding symmetry, which you can see in this expression here. Shifting X is the same as shifting phi hat. And this is some kind of a funny symmetry. The translation mixes with the winding symmetry.
So that only happens when lambda is sufficiently large?
But sufficiently small. I'm perturbing in lambda. So
if the lambda is sufficiently small.
I first set lambda equals 0, and then the chemical potential drops out because of spectral flow.
I asked the wrong question. For R large or for R small?
Any R, I claim that for any R, for Q large enough, regardless, so if R is sufficiently small or large, cosine phi hat is irrelevant, and then I don't need to answer your question. But even when R is such that cosine phi hat is relevant, still this operator does not affect the low energy physics.
And so it's only a symmetry in the limit Q goes to infinity?
Yeah, but I can take Q large enough, and that's good enough. This is
what are the symmetry violations? Again, power law in Q or exponentially small in Q?
Oh, it's exact. It's a function of Q as long as I'm looking at low energy states. I'm looking at low energy states below a certain energy, and if Q is large enough, the U1 symmetry becomes exact.
For any Q, there are certain correlation functions for which it's an exact symmetry.
That's correct.
I have a somewhat similar question. So if we just talk about the lattice translation, just without anything else, then we have in momentum space, we have momentum conservation up to something proportional to 1 over A. So now there's a question of what we mean by low energy, because of if we are scattering a few things at low energies, then it'll look exact. But if we scatter enough things at low energies, we can still violate it. So what is the latter process part of the low energy theory or not?
So the proper way to answer your question is to analyze this problem on the lattice. Everything is finite, everything is cut off, and we have done that in the paper. And there are many new ingredients. I took the path here that I do everything in the continuum, and then I don't have to address this particular question. But this is a very interesting question, what I mean by low energy. It's clear that if I look at the ground state, finite number of quanta, well, anything at low energies, the momenta are small, and the symmetry is exact. It's not that it's exact up to order 1 of the cube. It's an exact symmetry at low energies. So what
Imagine that though, few quanta is part of your definition somehow. Like it's exact so long as some of them.
I think I can actually take it beyond few quanta, as long as the momentum is low.
Right.
As long as the momentum, I totally have waves.
Right.
Yeah, the total, as long as the total momentum is low,
Then it's an exact state.
it's an exact state. Simply because it's averages.
Yeah, I guess what Nima was saying is that with many particles, you can make this high momentum.
That's right, but then it would cost you a lot of energy. You have a lot of particles.
Right. And energy of order is Q over L, right?
That's correct. Yeah. So if Q is large, so the way to think about it is imagine if you have a lattice, imagine that Q is a fraction of order 1 times per site. So per site, you have say 1/10 of charge 1/10, and you send L to infinity, helping the filling fraction, that's what it's called, fixed. And then the symmetry, in this limit, the symmetry is exact, which is surprising because there's no such symmetry in the UV. So how can we violate it? Operators like cosine phi hat, they might or might not be relevant, but they might or might not be relevant. That's the first thing you would think. They will break the winding symmetry, but they do not respect the UV translation symmetry. So they are not there. So they are there as operator, but they are not in the action. Operators like that are invariant under translations of the UV, but they're not invariant under translation of the IR theory. So that's a more symmetry way of saying it. I have half a dozen other ways of saying it, but I don't want to waste too much time on this. So the eminent symmetry is not violated by relevant or irrelevant operators. And it's really important that it's different than an accidental symmetry. So this thing is in between an emergent symmetry and an exact symmetry. Let me move to the second topic and discuss a lattice model. And that would be a lattice model of a free boson. This has a very, very long history of thousands of papers, but I'm going to take a particular path. It comes under the name of the XY model. The name XY model appears in the literature for 2 distinct models. So I'm not going to use this terminology because does not uniquely specify what we mean by the model. But instead of using the Euclidean formulation of classical statistical mechanics, I'll do it with a Hamiltonian formulation of the lattice. So this is the Hamiltonian. I have a lattice in 1 dimension. So there are sites and links. There's a momentum P at every site. And there's a circle valued field at every site phi, which is conjugate to P. So phi is circle valued. And okay, this is the Hamiltonian. Finite number of degrees of freedom because I have periodic boundary conditions on a finite lattice. Parameter beta, there's a U1 symmetry, which is similar to the momentum symmetry, shifting phi by constant, and there are a bunch of discrete symmetries that I will not discuss. There's no winding symmetry, and therefore there's no anomaly. In fact, when I first heard about this model many years ago, I heard that there cannot possibly be a winding symmetry, because if there is a winding symmetry on the lattice, then there would be an anomaly, and we know that we cannot have an anomaly on the lattice. And since we cannot have an anomaly on the lattice, it necessarily breaks the winding symmetry and all the physics that follows from it. What I've just said is incorrect. Let me demonstrate it. So what do we know about this model? For large beta, it flows to the quantum theory we discussed earlier with R squared equal to pi beta. So that's a conformal field theory. But for smaller values of beta, the model doesn't have a winding symmetry. It's the same as the model perturbed by cosine phi tilde that I described earlier. It's a relevant operator. The term in condensed matter physics is that the vortices proliferate and the system is gapped, and that's known as the BKT transition. So this is the same as the model with cosine phi tilde. Now, we would like to suppress the vortices because we would like to study the model with the winding symmetry, and we would like to study the model with the anomaly because we want to understand anomalies. How should we suppress the vortices? So this has a long history that I don't fully understand. As far as I know, the paper of Gross and Klebanov was the first that did it, but for all I know, they could have been earlier. So they had a way of doing it in Euclidean formulation of the model. We will follow the Hamiltonian formulation to do it. So we would like to suppress the vortices such that there will be no vortices at all. So what are we going to do? We're going to use a Villain formulation, and we write the following Hamiltonian. So the first term with p squared is just copied from what we had before. And instead of saying that phi is circle valued, we let phi at the sites be a real number and put on the links integer valued fields n, appears here. And instead of cosine, I'm just going to write delta phi minus 2 pi n squared. And when I say I think the first person who did that was Mr. Villain. So it's again long before I studied it. And we can think of it as being a gauge theory whose gauge group is n. So phi is the coordinate conjugate to p, or p is the momentum conjugate to phi. And the integer gauge field on the links is dual to an electric field, which is circle valued also on the links, which are conjugate to each other. So n is conjugate to the electric field. And since E is 2 pi periodic, I can add a cosine E to the Hamiltonian. This is the analog of E squared. So if you're not familiar with discrete gauge fields, for ordinary gauge fields, you have an E squared in the Lagrangian. And here, because it's circle valued, we write cosine E. So this is the Hamiltonian. And the physics of this Hamiltonian is very similar to the physics of the model I described before, where there was a cosine delta phi and we didn't have n and e. So this n and e, their job in life is to make phi effectively compact. Now, as a gauge theory, this model commutes with this operator. You can easily check using this commutation relation, it commutes with this operator. And therefore, we should impose Gauss' law at every point. So at every point, we should look at the big Hilbert space and impose this as an operator equation. This is Gauss' law at every point. So this is our model, and we can study it. And this model is essentially the same as the model on the previous slide with the cosine. This is the Villain version of that model. So a very, very deep insight in quotations. You want to suppress the vortices, set G to 0. If G is 0, there are no vortices. So that's what we're going to do. So we're going to study the same model for G equals 0. Looks completely trivial. So that's what we will study. This is the model. We call it modified Villain. It's quadratic. It's essentially solvable. It's exactly solvable, actually, because it's quadratic. And you can diagonalize the Hamiltonian. You can write all the states in the Hilbert space. It's completely solvable. And it has two U1 symmetries. It has a momentum symmetry, which is the charge, which is the sum of the momentum on all the sides. That's the same as it was before we messed it up with this phi and gauge field. More interesting, so this is the symmetry that we could see with the naked eye. The more interesting winding symmetry is we had the Z gauge field, whose gauge field is n. So we can study a Z-valued Wilson line. So the winding symmetry is the Wilson line. The Wilson line is a good symmetry operator, and it commutes with the Hamiltonian because we didn't have an E in the Hamiltonian. Normally, that's not a symmetry because there's a cosine E, but now we killed the cosine E, so that's a symmetry. And you can check that this operator, this winding, which is a sum of delta W, commutes with the Hamiltonian. And the sum here, the delta phi drops out, so it's a sum of integers, so the charge is an integer. So this model, as it stands, has both momentum and winding symmetry. On the lattice can have 7 sites, finite dimensional problem. The Hilbert space is infinite dimensional, but because we have number of rollers, but the number of rollers is finite. And it's straightforward to compute the commutator between J, W, and JM, between this and that. So the phi from here does not compute with the phi from here. So we get a non-zero answer, which is a Lattice version of the Schwinger term. So in the continuum, it's delta prime. On the lattice is its difference between two Kronecker deltas. So this is the model. It's completely finite, and it exhibits the anomaly. And furthermore, you can check that it has T-duality. You can perform exact T-duality on the lattice that exchanges phi with E in momentum and winding and equals R. So this model, this pedagogically is a good example because it does on the lattice everything that you know and love about the continuum, almost everything.
Let's see, the charges do commute, right?
The charges do commute. Whoops. Yeah, the charges do commute. The charges do commute because the delta phi drops in the charge. This is the same as in the continuum. In the continuum, the commutator is delta prime. So when you integrate it, it drops out. So the charges commute, but the currents do not commute. It's completely straightforward to do it. And you can define J without the delta phi such that they commute, but then it's not gauge invariant. It doesn't respect Gauss law. So there are many more details you can play with this. It's a very nice pedagogical model. But it does, on the lattice, whatever you knew in the continuum, with finite number of degrees of freedom. Of course, there's no divergence or anything. So how do we probe that there are anomalies? So we're going to say we have to turn on background gauge fields. And for simplicity, let the background gauge field be flat. So then how can we think of flat background gauge fields? There are several complementary ways of thinking about it. They're all equivalent to each other, and they all have their pros and cons. First, we turn on background gauge field, so we know what the current is, so we just couple the current to the background gauge field, and we can change the Hamiltonian everywhere due to the background field. That's option one. Slightly more interesting thing is to, using the fact that the background is flat, we don't change the Hamiltonian, we keep it as is, but we have twisted boundary conditions, which is the same as saying that we have some holonomy around the cycle.
Namely, the sum of integers n around the cycle.
Yeah, but I'm going to have another way of thinking about it, which I find much more physical.
Yes, this is a question of whether to put the gauge field in the time direction or space direction.
No, we should do both. Should put both in space and in time. I'm going to put both in space. Let's first start with space.
Option one.
I'm starting with space. Let's just put it in space. We can later worry about time. Not later. We will discuss gauge fields in the time direction. But so far, we just put background field in space. And we would like to describe what does background field in space mean. Either we put one on every link, or we pick a gauge such that it's all localized on one link. That's a gauge transformation. And when it's all localized on one link, I can say that it is in the transition function, or I can say the transition function is trivial, but I modify the Hamiltonian. And that's the way I prefer. So that's actually a very common thing to do these days, is to view the background field as a topological defect. The transition function of the gauge field is replaced by a topological defect. I also make it more explicit. So we keep the periodic boundary conditions as they were before. We keep the Hamiltonian as it was before, except that we make a local change in the Hamiltonian. So the physics is exactly the same everywhere. The Hilbert space is exactly the same. We just change the Hamiltonian in one neighborhood. So the global symmetry with the defect might or might not be projective, independent, might be realized projectively or not, independently of what it did in the original Hilbert space. So even if the original Hilbert space gave a linear representation of the global symmetry, now the Hilbert space with the defect will give us a projective representation, which will be the hallmark, will be one of the hallmarks of the anomaly. So we said in quantum mechanics, an anomaly is the Hilbert space is in the projective representation. What we see here is that if we put the Hamiltonian is not, the standard system is not in a projective representation, but if we put these defects, it is in a projective representation. So let's do it very explicitly. And again, the model remains solvable if I do that. So a momentum defect, I take one of the links, and I had this thing here. And I just put a constant eta on that link. Somebody before said, I think Igor said that to make ends, some of the ends will not be an integer, but will be a fraction. So I keep the n's integer and I write the fraction explicitly on one of the links. And for the winding symmetry, I just shift the Hamiltonian over there, here, P, by shifting P by a constant. So these are all the changes. So now I can study the problem with the defect, momentum and winding defects. And I had to choose a point where I change the Hamiltonian. But the point is that it doesn't matter where I put them.
Sorry, what's the difference between eta sub m and eta sub w? Those are two different constants?
That's correct. One of them, it measures the strength of the momentum defect, hence the subscript. And the other measures the strength of the winding defect, hence the subscript w.
Okay, so you're changing the symmetry action of the global symmetry, is that right?
No. There's a symmetry is U1 momentum times U1 winding, and I introduce a defect for the momentum and winding. They are labeled by.
Sorry, this is a change in the Hamiltonian.
That's a change of the Hamiltonian.
With two free parameters.
There are more than two, because I can put it in many different sites and many different links.
For one defect, it's two free
I
parameters.
can also distribute the, put omega eta over 2 here and another eta over 2 there. So I can spread it in many different ways. And now I'm going to check whether all these ways of spreading the defect gives the same answer or not. And most of the changes, they are the same, because it's straightforward to see that we can conjugate this Hamiltonian and move the location of the one point to another, or from one link to another. That's just a unitary transformation of the Hamiltonian. In fancy language, we're just doing a gauge transformation in the segment that we want to shift. More mathematically, we change the trivialization of the bundle that we had by shifting the end of the patch and where the transition function resides. Anyway, you think about it, that's the answer you get. And hence the defect is topological. However, okay, so we have these defects, we can fuse them, we can move them around. All of these things are unitary transformation, are done by unitary transformations. And that's why the defects are topological. However, there's an interesting however, when I move the defects around and they cross, then the answer changes. So when I move, this is the momentum defect, and this is the winding defect. So I first move the winding defect, and then the momentum defect, or I do it in the opposite order. And if you look at these unitary transformations, and you do that, the unitary transformations depend on the currents. Since the currents do not commute, these two operations do not commute. So what we see here is that moving this pair from here to here in two different ways, either sliding them this way or that way, then we get different answers. They differ by phase. And that phase is the mixed anomaly between momentum and winding. I deliberately discuss it in this language, although we could have discussed it in many other ways, because we're going to use exactly this way of this reasoning in a different model, which is much more subtle.
So on the right-hand side, your figure, the world lines intersect 2 times. What happens if they intersect only once?
They don't intersect at all on the left-hand side.
On the right-hand side?
On the right-hand side, they intersect twice.
What if they intersect only once? Can't you do a world line like that?
And then you can do that also. And so you should really do it. There's a much more general thing you can do, moving, splitting it to 2 different defects and fusing them together. There are many more things you could do. The nice thing here is like the starting point and the end point is exactly the same. I just slide everything to the right. And depending on how I slide them to the right, I get a different answer.
Okay, I see. Okay, thanks.
In the other ways, you said it, I don't end up in the same point. It says, okay, so I can't compare. Thank you for the questions, Greg. So let's discuss the anomaly further. We can show, I'm not going to do it here, that the momentum defect labeled by eta m carries winding charge, and the winding defect carries momentum charge. Okay, sorry, and the winding defect carries momentum charge. And they can carry fractional charges as one would expect. Now, there's a fine print here because we can redefine what we mean by charge and absorb this fractional value there, but then it would show up elsewhere. This is common. Let's discuss translation. The model with L sides is a ZL translation symmetry. There's also parity, but we're not discussing. We can add parity to the story, but let's not do it here. And it is generated by an operator T whose Lth power is 1, because this is what takes us around the circle. When we put the defect, that's not true, because when we slide the system by one side, the defect is no longer where it was. But that's not a big deal, because we learned that the defect is topological. So we can bring it back to where it was before using the unitary transformation. So even though symmetry T, the symmetry operator T, the symmetry operator T does not commute with the Hamiltonian, we can dress it in such a way by combining it with the unitary transformation such that it does commute with the Hamiltonian. So the original translation is not a symmetry, but there is a modified translation which does commute with the Hamiltonian. What algebra does it satisfy? It's explicit computation, and you can show that this new T raised to the Lth power is not 1. Part of it is straightforward and part of it is solved. What does it mean to take an operator all the way around space? We can think of it as having twisted boundary conditions. So as we go all the way around space, we undergo a global symmetry transformation. So what the defect tells us is that when we take T to the Lth power, what we should have on the right-hand side is the symmetry transformation that we used. So twisted boundary conditions mean that if you do translation around all of space, you don't come back to where you started, but you come back to where you started, multiplying by the group symmetry transformation. But when you do this computation here, you see that this is not quite right. There is another correction factor, which is a phase, which is another signal of the same anomaly. So the first factor is related to, the first two factors are related to the twist. And the second phase is the anomalous phase, telling us that in another way of probing the anomaly. So we see that we can probe the anomaly many different ways, the commutation of the currents, in this way, which I really prefer, using defects and their properties, and especially what happens when I drag things around a lattice. This brings me to the last topic of this talk, and that's the Heisenberg chain. So there are trillions of references. I decided not to give them. So we have a chain of qubits.
Wait, sorry, Nadia, before you move on to the next topic. I thought this is a talk on eminent symmetry. So I'm missing the main point. So you've now shown that moving defects, you detect this anomaly.
I didn't say anything.
Is there an eminent symmetry here?
This system doesn't have any eminent symmetry, and
okay.
I shouldn't discuss that.
You're just discussing anomalies at that point.
That's right. So now I'm going to put all the ingredients together and discuss a system that has both anomalies and an eminent symmetry. And that's the Heisenberg chain. So we have spins at every site, spin a half, and we have nearest neighbors. We can put next to nearest neighbors and so forth. All that I care about is there is an SO3 symmetry. And this model knows to flow the long distances to the gapless SU2 level 1 WZW bar. And if L is even, the total Hilbert space is in some representation of SO3 because there's an even number of doublets. If L is odd, the total Hilbert space is in a half integer representation of SO3, or precisely of SU2. It is in a projective representation of SO3. So the case of L even and L odd are different, and indeed they flow to different systems at long distances. Locally, they are the same, but globally they're not. L even takes us to SU2 level 1, and L odd takes us to the twisted theory where we twist by the Z2. And I can tell you more about that theory. The SO3 inside the macroscopic SO4 is realized projectively. So this system has anomalies.
Macroscopic SO4.
So at short distances, we have SO3. At long distances, it's the SU2WZW model, which has an SO4 global symmetry. It's SU2 left and SU2 right divided by Z2. This SO4 is realized projectively in the twisted Hilbert space. The spectrum is a half 0 plus 0 a half in terms of Coulomb representations. So I'm going to present it as anomalies, but there's huge literature on the subject. This is a tiny fraction of them. starting with the classic work of Lieb-Schultz-Mattis, although I checked that the word anomaly does not appear in that paper. In fact, the word anomaly does not appear in most of the papers in this list, except the more modern ones. So what does this have to do with anomalies? So before I continue, I should say that what these papers tell us, so the original papers have exact analysis of the lattice model. What I'll do is kind of be similar to that. Oshikawa then streamlined it, Hastings extended it to higher dimensions, and these other authors described it as various, felt that it feels like an anomaly. I constantly go around asking anomaly what? There's no anomaly. And to the extent there is an anomaly, it is an anomaly in translation. But we all know that there's no anomaly in translation. So what's going on here? And I'm going to answer this question. So we'll study anomalies using flat background gauge fields. So we're going to follow the same strategy as before. Namely, we couple the system to flat SO3 background gauge fields, and we're going to represent it as defect and study the system with a defect. So let's start with space. Space, we can have an SO3 element. We can go conjugate it to be of the form e to the I sigma z, where sigma is the same as sigma plus 2 pi, and sigma is the same as minus sigma. We can put it in any direction of the group using conjugation. So that's what we do in space. We have twisted boundary conditions, or we change the Hamiltonian. So we will change the Hamiltonian and put the link, add the link labeled by J. We are going to change the Hamiltonian. So for link not equal to J, we have the standard Hamiltonian, and at one link, we change by twisting by sigma. So that's the Hamiltonian. And the defect is topological. We can change the value of J by conjugating the Hamiltonian by a unitary transformation. It's exactly as before. We can shift the position of the defect just by a unitary transformation. So it doesn't matter where we put the defect. And for generic sigma, the SO3 global symmetry is explicitly broken. And the remaining symmetry, which is unbroken, or mathematically the centralizer, is U1. Because we can still rotate around the z-axis by a phase c. And as we said before, the defect breaks translation because we pick the link J. We pick the link J where the defect is. So if you're going to shift, like shift transformation, the defect is no longer a J, but it is a J plus 1. But we can do a unitary transformation to bring it back to where it was. So this operator commutes with the Hamiltonian. The original one, the original T doesn't, but this dress translation commutes with the Hamiltonian. But it satisfies some interesting properties. If you raise it to the nth power, we get e to the I sigma sz. That's good. That's what twisted boundary conditions mean. We go all the way around. We undergo a transformation by e to the I sigma sz. But surprisingly, even though the Hamiltonian is invariant and the sigma goes to sigma plus 2 pi, the operator T is not invariant and the sigma goes to sigma plus 2 pi. We get a minus sign. We can change it by shifting here by I sigma over 2, but then this equation will be messed up. So let's continue with this convention and then we'll see what freedom we have. So this is the Hamiltonian. And now we're going to compute the partition function. So what are we going to compute? We have e to the minus beta h. This is this Hamiltonian. L is finite. Everything is finite. We're raising translation to the nth power. So we can compute trace with t to the n, which means that as we glue in the Euclidean space, we shift by n sites. And this is can be thought of as the background gauge field in the time direction. So somebody asked me before, I think one asked me about gauge fields in the time direction. So this is a flat background gauge field, which is labeled by two parameters. Sigma is the holonomy in space, and xi is the holonomy in time. And there are some identifications because we can conjugate it. Right? So this is the space of flat SO3 connections, except that we do it here on the lattice. And crucially, we also have this lattice translation operator. So this is the partition function. And I wrote a particular Hamiltonian that we can now add next to nearest neighbors, next to nearest neighbors, add whatever terms you want, as long as the SO3 symmetry is preserved. Everything I say is still correct. So this is like a background gauge field for SO3. And N probes Lattice translation. One might be able to think about it as a gauge field for Lattice translation. I don't fully understand what that means, so I'm not going to follow that route. And let's say here it's not precise, and T to the L satisfies that. So we're going to explore this partition function. So that's what we're going to compute. Compute is a strong word. We just explore some of its properties. And this looks like a mouthful, but let me guide you through that. First, let's compare sigma with sigma plus 2 pi. We already said that T, the translation picks a minus sign, and the sigma goes to sigma plus 2 pi. So we get here -1 to the number of T's. That's it. If we shift Xi by 2 pi, we get a factor of -1 to the number of sites, because we said that when the number of sites is even or odd, the Hilbert space is in the linear or projective representations of SO3. If we shift N by L, that's the same as shifting Xi by sigma, because we said that T to the L is E to the I sigma. That's known that if this is the analog of tau goes to tau plus 1 or the torus. So when we have twist in space, tau goes to tau plus 1, we also need to produce a twist in time. If we conjugate the whole thing by a Z2 in SO3 that reflects inside the rotation angle, sigma in Xi are the same as minus sigma in minus Xi. And finally, we can use parity and relate N in Xi to minus N in minus Xi. So you have a bunch of identities, and there might be others, but that's what you get of this thing. But it's independent, I emphasize, it's independent of the Hamiltonian. The heroes of the story are these two phases here in purple. They are the heroes of the story. And we can redefine the operators and change them. We can redefine the operators and change the phases. But if we remove the phases from here, they will show up here. So if you look at this collection of identities, these phases from here and here are unavoidable. There's no way to remove the phases. If it starts sounding like an anomaly, it is because it is. So naively, these phases shouldn't be there, because what we did was just describe the same background in two different ways, but they are there. And they mean that Z is not quite a function on the parameter space. I can say more about that more mathematically, but let's skip that. So we can redefine the operators. As I said, that's the same as adding counter terms and move the phases around, but we cannot get rid of them completely. And what we see here is a mixed anomaly between the internal SO3 symmetry and the Lattice translation ZA. That's what we see. We are trying to put the system in the background SOL, and we see that the ZL symmetry should act, the SO3 symmetry should act, but something acts projectively. We have phases that we cannot get rid of. I'll soon say that in a bunch of different ways. Depending on your point of view, you might prefer one or the other.
Does this have a manifestation in the continuum?
Yes. Yes, I'm getting there. So what the question one is asking, let me phrase it. We are finite L. This is true in a lattice with one site. It's true for a lattice with two sites. Everything I said, I don't care with this. Look at how many sites we have. This is the UV. So in the spirit of the truth, we can ask, what do we have in the infrared that saturates this anomaly? And it looks puzzling because it's SO3. Okay, we see the SO3 in the continuum, but there's no mixed anomaly between the SO3 and translation in the infrared. So how are we going to saturate that in the infrared? I guess this is what you have in mind. I'm going to answer this question.
If you couple to a background SU2 gauge field, do you get rid of the anomaly?
The background, it was very important that the background was SO3 and not SU2.
So that's what I'm asking. If you introduced a background SU2, would there be an anomaly?
That would mean that you cannot, that this -1 to the N and -1 to the L are not there.
Yeah.
View it as SO3, then you can distinguish sigma and sigma plus 2 pi. The SU2 you cannot. These are putting words on it. There is a Hamiltonian, the function of sigma. Hamiltonian is the same for sigma and sigma plus 2 pi. Yet the partition functions are not the same. But it's the same Hamiltonian. I computed, it's the same Hamiltonian we computed the trace. And that is this is an SO3 background, regardless of how you want to think about it. So the relation depends only on the Hilbert space and the global symmetry, not the details of H. In particular, they are independent of beta. So now we go to low energies. And before we get into the details of what actually happens, we already see that the low energy theory cannot be completely trivial, because we should get the same minus signs in the low energy theory. The low energy theory should be smart enough that as we shift sigma, xc, etc., it reproduces all these minus signs. So it cannot be completely trivial. And there are two logical options. Either the ZL translation is spontaneously broken, or the model is gapless. In fact, this was exactly the conclusion of Lieb-Schultz-Mattis many years ago. So we reproduce their answer. And if you look at their reasoning, almost every step there has a counterpart in our discussion, although the big picture looks completely different. So this is the qualitative conclusion, but we would like to say better than that and see exactly how it's realized and how do we compute exactly these minus signs in the continuum. Before we do that, just say that this is easily generalized. Instead of SO3, it's enough to consider an O2 subgroup of it. And you might be nervous that we use sigma as a continuous variables. With a little bit more work, it's enough to consider Z2 times Z2 out of the O2, and the reasoning still goes through. So you can even use a discrete group, a finite discrete group, and it's still true. And you can extend it to higher dimensions, and we also analyze many other examples. Make sure that we know what we're doing. In order to address the question of how to see it in the IR, let me first generalize the model. And that model is known as the XXZ model. So for lambda z equals 1, it's the previous model, but now it's a one parameter family of models. It's also exactly integrable, solved sometimes in the 70s or 80s. The global symmetry is only O2. For lambda z between -1 and 1, it flows to the compact boson theory with radius larger or equal than 1 in by conventions. In the previous discussion is essentially the same. You could just follow all the steps and you would see that you could just copy everything. It's exactly the same. But that leads to a question. This model has a smaller symmetry. It flows to the C equals 1 model. It doesn't have a winding symmetry. Why doesn't it have a BKT transition where it should have? In other words, cosine phi tilde preserves G, this O2 symmetry. And depending on lambda z, it might or might not be relevant. So why is this is the low energy answer? In fact, you could have asked me the same question already at the SU2 point, which we discussed earlier. The SU2 point, we classify the operators according to the SO3 global symmetry. To classify the operators according to the SO3 global symmetry, then the low energy spectrum includes an operator, which is SO3 invariant and has dimension a quarter. There's a very relevant operator in the infrared, preserving all the symmetries in the UV, but it's not activated in the action. So you could have asked me the same question there. Why is the answer for the SO3 spin chain, why is it the SU2WZW model given that there is no symmetry that prevents the operator of dimension a quarter, which is invariant on the older symmetries in the problem? I claim that this is the low energy theory. This is exactly the model we discussed before. And the crucial point is this factor of 2 here. This is the crucial point, the factor of 2. So this model has an eminent Z2 symmetry. So the low energy theory is not just the C equals 1 model perturbed by some winding operators, but it's perturbed by winding operators only with even winding charges. No term cosine, so there are operators cosine n phi tilde with odd n. There are such operators in the theory, but they are not present in the low energy action. So this is the low energy theory.
Did you have to add a fugacity for charge in order to see the eminent symmetry?
No, I just said this thing, I'm going to argue that this is the right answer, and I'm going to prove that this is the right answer. There before the story with the fugacity was an example how you can get an eminent U1 winding without putting it in by hand. So now it's a different system. I don't even put the chemical potential. Just have the C equals 1 model, except that I perturb it not by cosine phi tilde, but by cosine 2 phi tilde. And the claim is that this is the low energy limit of the spin chain. So that's a claim. I haven't shown it yet.
I'm losing the logic. You had HJ, H upper capital J, where you of sigma, and then you found interesting properties about its partition function when you introduced a flat SO3 gauge field.
Yes.
Then you introduced the XXZ chain.
No, I did that. I said there were phases, and then I wanted to answer, and as a result, I reproduced LSM, namely that there are two options. Either it's gapless or the Z-Ellis translation symmetry is spontaneously broken. Then I put that aside and say, let's consider another model.
Okay.
The XXZ chain. It's a one parameter family generalization of the Heisenberg chain. And I claim that at low energy, and I asked the question, why does this model flow to, why does the original model flow to the SU2WZW model? And also here, why don't we have the VKT transition in this model? And I claim that this is the low energy theory. The low energy theory has a winding operator with charge 2 in the action, but not with charge 1. And even irrelevant operators with odd charge are not present. So to see this eminent symmetry, I claim that the microscopic translation operator.
Question. So the perturbative dimension of cosine 2 phi tilde is 1, 1, right?
At which point? At the SU2 point, it's 1, 1. At the SU2
I'm a little
point,
confused because then doesn't it flow? I mean, that point is not exactly.
okay, so we can discuss that in a lot of detail. As if you sit at the SU2 point, it doesn't. If you look at it in one direction, it's irrelevant. If you look at it in the other direction, it is irrelevant. But if you are exactly at the point, it doesn't flow.
That's the standard BKT flow.
It's a standard BKT, but for
But you're
another.
at a very fine-tuned point.
Well, it's the end of the line. There's a one parameter family lambda. And I first crossed the original BKT point and nothing happens. That's not fine tuning. When I cross and the claim is that there's a Z2 eminent symmetry. That's as I cross the first one. Then it breaks down and it has another BKT at another value of R, which is R equals 1. That's where I have a new BKT, but it's not the original BKT,
Yeah.
which is at the R equals 2. Yeah.
Where it's breaking down, it's probably where it's becoming, where it's trying to break the Z2, so to speak. The XXZ model has an easy axis and has a hard, well, it has a plane and it's got a perpendicular line.
Yes.
The sign of the coupling determines which direction of the magnetization is favored. And one of the two is probably the relevant one.
Well, the transition is when it's 1, not when it's 0.
When it's one, they're equal. And not on opposite.
Oh,
sides.
okay, good.
It's from this way.
That from this point of view, but from the conformal field theory point of view, in one direct for one side, cosine 2 phi tilde is relevant, and the other side it is
Well, I
irrelevant.
was just trying to make contact with this.
I should say that this model was exactly solved using Bethe ansatz. So there's an exact solution of this model. And this function R of Z is known, it's given by some tangent or something. So there's an exact solution here. So yeah, and there are lots of physical, there are trillions of papers discussing it from any perspective. This interpretation is a nice one, but the main thing, which is really the question that one asked Greg, and I'm going to say that is now to address this particular puzzle. We know that there must be a resolution because the model was exactly solved. So we need to address this puzzle. And the resolution is that this is the answer. I just have to prove that this is right. I claim that this is the answer. And the low energy limit, the XXZ chain, is the free boson, but not perturbed with winding number 1, but with winding number 2, so that there is a Z2 symmetry. And to see that, we should look at lattice translation in more detail. Naively, lattice translation goes in the continuum limit to e to the 2 pi I, the momentum of the continuum theory divided by the number of sites. That's true when t is raised to an even power. If you just take the continuum limit and look carefully, you see that t is a phase, but it does not approach 1 in the continuum limit. T square, actually it's T to the fourth approaches 1 in the continuum limit, but T itself doesn't. So T, the lattice translation, is expressed in the continuum limit as C inverse, some operator C, times e to the 2 pi I P over L. P is the momentum of the continuum theory, and C is identified as the Z2 symmetry of the continuum theory. That's a claim. So on the lattice, only T is well defined. C and P are not well defined on the lattice because I can move out of C into P, right? Only their product is well defined. But if I'm in the continuum limit and I limit myself to P's which are small, I cannot shift the phase of order 1 from C into the other phase. And this is true only already on the lattice. If L is large but finite, say 1,000, now I'm looking at the first, say 100 states, there's an unambiguous decomposition of T into such a product of 2 factors. So on the lattice, only T is well defined, but at low energies, P and C are separately well defined. Furthermore, this relation is exact. Normally, when you have relations between the lattice and the continuum, they are violated by terms of order 1 over the lattice by the number of sides square or the number of sides to the fourth, etc., higher powers of T. But this T to the nth power must be exactly 1. And since it has to be exactly 1, there cannot be any high order correction. So taking the continuum answers, we can actually compute T on the lattice and derive exact results for the lattice system, confirming our picture. So there's something exact about this C, and this C generates an eminent symmetry, not an emergent symmetry. So this transformation of shift by one side goes over in the continuum limit to a Z2 internal symmetry. And it's not an emergent Z2, but it's an eminent Z2. So now we can look at the answer. For L even, we find the compound boson conformal field theory with the radius we discussed. And L odd, we get the same theory, twisted by this Z2 element. So it is as if adding another side is twisting by lattice translation. So the U1 and the Z2 are realized projectively. In particular, C square is -1 in the twisted theory. This can be checked both on the lattice and in the continuum. This means that the eminent Z2 is a mixed anomaly with the SO3. This way I resolve the puzzle that one asked me before. On the lattice, there's a mixed anomaly between translation and SO3. I'm almost finished, or you kick me out. So there's a mixed anomaly between ZL and SO3. In the continuum, the ZL becomes an eminent Z2 in translation, and the mixed anomaly on the lattice becomes a mixed anomaly between the SO3 and the eminent Z2 on the between the SO3 and the eminent Z2 of the continuum theory. So what happens in the continuum is there is a U1 or SO3, there is a new Z2 that we got for free, and the anomaly is a mixed anomaly between them, which is no. So this anomaly is the continuum limit of the LSM anomaly.
So I feel like I didn't follow this discussion of L even and L odd. Shouldn't the difference disappear in the infrared?
The difference is only the boundary conditions. So you can study the conformal field theory. Let's do it in the SU2 case. With the boundary conditions, so we are in the continuum.
Okay, it was the same continuum theory, but with 2 different boundary conditions.
That's correct. And the twisted boundary conditions are such that the SU2 times SU2 mod Z2 of the WZW model is realized projectively. And you can match that with, so you can check this formula, for instance, start from the continuum, look at this picture, compute the eigenvalues of the low-lying states, substitute in this, and find the eigenvalues of T, and match that with a lattice. In fact, it works also for a lattice of 2 sides, 3, 4, numerical lattice.
Related stuff is also true just for the XY model, right? You get different spin structures.
The XY model is a free model, so there's a similar thing, but there it's a little bit more surprising, less surprising, if you're exactly at the, because there the model is, with this particular Hamiltonian, it's free. So you can just diagonalize the Hamiltonian. This model is not free. Another way of saying it, if you took the XY model and you deformed the Hamiltonian, added more terms with respect to symmetries, then it's no longer free, so you cannot calculate, but this formula is still exact. This formula is still exact. It doesn't depend on this deformation. Intuitively, once you got this formula, it must be exact, because when you come to compute the eigenvalues of T, the states, T to the L is 1. Small deformations of the Hamiltonian are going to change the energy, because that's continuous, but they're not going to change the eigenvalues of T because they are phases. Fixed L root of unity. So as a more subtle dependence, which I did not discuss here, the things depend not only on L mod 2, but on L mod 4. And that reflects the self-anomaly of the pure eminent Z2. And I will not discuss it here. There's a long discussion in our paper. So in summary, before I'm kicked out, microscopic translations can lead to an eminent symmetry. That by itself, for me, was a surprise, although I knew about staggered fermions, I knew about the Fermi surface and so forth, but I'm still have not yet completely digested the fact that we have a symmetry which is not exact at short distances, and it appears exact at long distances at low energies, not approximate, but exact. And it's not that it's violated by higher power, suppressed by powers of the cutoff. It's not suppressed at all. And here I gave a number of examples of that. Anomalies are not specific to fermions or an infinite number of degrees of freedom. I showed an example of one qubit. I showed another example of a finite dimensional chain with anomalies. They do not signal the inconsistency of the theory. There's nothing wrong with the theory. The theory is perfectly consistent. And there's no need to add the bulk. The bulk can be a convenient thing to add in order to analyze it, but it's not essential for ensuring the consistency of the theory. Lattice models can exhibit anomalies. We discussed that at length, and that's true even for finite lattices. There's a lattice with 2 sides, 3 sides, 4 sides, and it exhibits the same anomalies that we know in loving the continuum. And anomalies involving lattice translation can lead to anomalies in eminent symmetries. So this way we tie together eminent symmetry from the first bullet to the anomalies we discussed here. So the anomalies, lattice translations manifest themselves as anomalies leading with the eminent symmetries. In this way, we connect to Lieb-Schultz-Mattis type theorems. I discussed a little bit filling constraints. There's a lot more that can be said about that, connecting to Luttinger theorem and filling constraints. So for me personally, this was a way of learning about LSM, learning about Luttinger, understanding how they have something to do with the anomalies that we know and love. And of course, it's also connected to SPT phases and because of through the connection of the anomalies. So it's one kind of story that puts together a lot of known facts. So I'll stop here. Thank you.
Please, go ahead.
There is a variant of the models that you described here, essentially Heisenberg anti-ferromagnet for it's related to Heisenberg anti-ferromagnet, but going to higher spin, in which the ground state dimerizes. So the long distance behavior actually exhibits long range order, but it's a staggered one. The energy of the odd and even located terms are different. In new language, so long distance behavior can be described by position plus just a binary degree of freedom. Would that be an example of?
I do not know this model. I'm not familiar with this model, but from the way you described, it smells like this language would be the perfect for it. Yeah, it would be a prime example for that. The Heisenberg chain is already doing it.
The Heisenberg chain for spin 1/2, the energy can be presented as essentially projection onto the singlet of 2 neighbors.
That's correct.
Now, if you increase the spin but keep that definition of the energy, you cannot singlet project to the neighbor with the neighbor to the right and to the left. So actually, you can prove that the ground state dimerizes, and then you have exactly what you are talking about in a very strict and simple way.
So it sounds like the lattice so in the Heisenberg chain, lattice translation by one side is one behavior, but with two sides,
Right.
it's kind of, this goes over smoothly to the continuum limit. And I think what you're saying here suggests that, I don't know anything.
But both goes mostly to the continuum limit, but there's an additional degree of freedom, even or odd.
So that's what happens, say, in the staggered fermions. In the staggered fermions, you get two species localized in two different regions of the Brillouin zone. Two ends of the Brillouin zone lead to two different species, say left movers and right movers. Even the number of species is doubled. And it sounds to me, I don't know your model, but it sounds to me like this is right, and B, with this language, it would be nice to analyze it. Because here we basically reduced it to a cookbook. You know, what's the symmetry, reduce the twist, what's the remaining symmetry, compute the partition function, write identities that should be satisfied. There are phases, that's the anomaly.
The picture is very simple, just dimerization. Think of minimal, nominal patterns. But it's a ground state of a Heisenberg type spin chain.
Please send me a link for a paper. I'd love to see that.
In your model, negative lambda was antiparamagnet, right? Lambda being negative is
What's lambda?
the coupling, the sigma z coupling.
In the XSZ model.
Yeah.
So lambda is between -1 and 1.
Yeah, but
One sign is ferromagnetic, the other antiferromagnetic.
No, they're all antiferromagnetic. Because there's an XX and YY with coefficient 1, and that is just the Z part that changes. That's why I didn't understand Edward's question, because I think he meant relative to the SU2 point, rather than lambda the way I described it.
I think it's antiferromagnetic.
It's antiferromagnetic for any lambda.
In one case, it lives on a circle, in the other case, it lives on the perpendicular line. So one is more like an Ising model, one is more like the XY model.
Can you elaborate on this?
You have the magnetization in 3 dimensions, in the X, Y, or Z direction. Depending on whether your coupling is bigger or less than 1, the magnetization classically is favored to be up and down, which is like a Z2 model, or in the plane, which is like an XY model. The XY model will try to flow in the infrared to an XY model. But the up-down guy will try to spontaneously break the Z2 in the infrared, which I think is the picture you see.
Yeah, that sounds very good. But it's still not clear that the Z2 that is spontaneously broken, that is not subgroup of SO3. It started first of all, it's not a symmetry of the model, but the Z2 that is spontaneously broken started its life as lattice translation. It's lattice translation by one side. So it's not part of the SO3 rotation. That's why I'm puzzled.
I understand your statement. Of course, in SU2, you can't change the spin from Z to -Z. You have to also make a reflection of the normal plane. So the model with the internal do a pi rotation around the x-axis. So
It's important, it's an antiferromagnet.
it's certainly important.
So
Everything
then-
I said, that's the
So everything is crucial.
So it's not the Ising mode, it's antiferromagnetic Ising.
Okay,
So
well-
then the
yeah.
spontaneous symmetry breaking then,
Thank you.
well, it's related to the Z.
What Juan is saying is important.
Okay, in everything I said, the fact that it's an antiferromagnet rather than a ferromagnet is crucial. Otherwise, it's not true. And yeah, there are various ways of seeing it.
Well, the statements about the anomaly are still true, but the low energy physics is.
That's correct. The mixed anomaly between ZL and SO3 doesn't care what the Hamiltonian is. You can flip the sign of the Hamiltonian, and all these identities ahead are exactly the same. You can set the Hamiltonian to be 0 or anything that preserves the SO3. So the anomaly is still the same.
Because you mentioned the magic term, Jordan-Wigner, right?
Well, that's only in the XY point. We can do Jordan-Wigner translation of that. I'm writing a paper with Shuhail, doing the same thing for fermions. And surprisingly, it's incredibly more subtle for a variety of reasons. And then we analyze in detail the Jordan-Wigner way of thinking about it. The key thing in the Jordan-Wigner is that in superficial studies of Jordan-Wigner, there's a tail that goes to infinity. But I would like to work at finite L. So the tail goes somewhere, and you have to pay attention to what happens at the end of the tail. And yeah, there's a lot of marvelous features, a lot of marvelous physics there, which I'm not going to discuss.
Okay, do we have any final questions?
Yes, yes, you do. Nadi, could you go back to 27, slide 27?
27.
Yeah. So I just want to make sure I understand why is C not emergent in the infrared? I thought it was exact on states with energies less than 1 over L, but in the infrared, L is infinity. So why isn't it an exact symmetry on all states, therefore an emergent symmetry? So I'm missing something.
If you look at the, oh, here, yeah. So Greg, you're very powerful. You diagonalize the Hamiltonian. That's the energy. And that's, let's call it whatever, alpha, where T is into the I alpha, that's 2 pi, and that's pi. Okay? Can you see?
Yeah.
Good. This is pi, this is my pi. I think by now you recognize my pi's. So many years. Okay, so Greg is very powerful, and Greg diagonalizes the Hamiltonian, puts it on the computer, I don't know, it just diagonalizes. And the spectrum of states looks like this. And let L be even for simplicity. That's an exact diagonalization of the Hamiltonian. That's what the spectrum looks like. So there are states whose energy, whose momentum is near 0, and there are states whose momentum is near pi. But that's not what an IR person says. An IR person says momentum is the deviation here for the 1 over L. There's an integer divided by L, and that's the momentum here. That's what an infrared person says. And this is very large momentum for the pi. And it's kind of very, very large in the continuum limit. But again, there are changes here for the 1 over L. So the infrared person would say, look, these are really 2 species, exactly the same as, like I said, there are two kinds of states. There are states which are in this cone and states which are in this cone. And I'm going to label the states in this cone as being odd and the states in this cone as being even. And what I call momentum under continuum translation as opposed to lattice translation, whose eigenvalue is these numbers here, which are for the 1 over A. So as long as I'm in low energy states, say up to here, I could say that this guy has small momentum and it carries for the Z2, it carries mine, it's odd. But there's also a perverse way of saying it. No, it's really even under the Z2, but it has a very large momentum from here. But that would be perverse. So as long as I'm in low energies, there's for every state in the Hilbert space, I can assign a Z2 charge and a momentum for the 1 in continuum units. That's not true for high energy states. For the state of around here, should I say that it is from this cone or from that cone? There's no natural way to answer that.
Yeah, but don't those go away in the infrared limit? That's what's confusing me.
That's right.
Why is it not just an emergent symmetry? That's what I don't understand.
Emergent symmetry has 2 characteristics. Number 1, it is there because there is no relevant operator transforming under it. And if you write an effective action following the standard rules of effective action, putting all possible operators that are allowed by the microscopic symmetry, you would say that there's a relevant operator transforming under it, adding to the action, it completely ruins the story. That's number 1. Number 2, even if you're lucky and there is no relevant operator transforming under it, there could be irrelevant operators. So if you go a little bit higher up in energy, you're going to see that the symmetry is not exact. That's why we have proton decay in the real world. So the upshot is that an emergent symmetry is a symmetry that is not there in the UV. If you wish, it is in the co-kernel of the homomorphism from GUV to GIR. It's in the co-kernel. It is not there in the IR. And it is characterized by these two ingredients. No relevant operator. There is no relevant operator. There does not exist a relevant operator transforming under it. And there are relevant operators transforming under it, and they are present in the action. That's not true here. That's not true here. What happens here is that there can be relevant operators transforming under it, but they're not present in the action. And similarly, there are irrelevant operators transforming under it, and they are also not present in the effective action. So a low energy person would say that the symmetry is really an exact symmetry. There are relevant operators transforming under it, but they're not in the action. And there are irrelevant operators transforming under it, but they're also not in the action. So from the low energy point of view, the symmetry is an exact symmetry. From the high energy point of view, the symmetry was never there. Now, I can describe it in more detail theoretically where it came from, because it really emanates from the microscopic translation. And it arises or emanates from an interesting interplay between UV translation and IR translation. They are not the same. And we see it here. Under UV translation, I cannot even separate whether this has a low momentum or a high momentum. In terms of the IR translation, the momentum is the low value. And there's another Z2, which tells me whether I'm here or here. Now, that's not new. You look at the Fermi surface and the two guys at the two ends, you measure momentum relative to the end of the Fermi surface, and you say it's left moving or right moving, depending on whether they're on the left end or the right end. And the same thing is true for a Kogut-Susskind fermion. It's a Brillouin zone, and there are species at the left and then the right, and there's an eminent Z2, non-emergent Z2. And if you ask, why isn't there a master? What protects the master? Macroscopically, there's a Z2 chiral symmetry. Microscopically, it's lattice translation. So in the case of staggered fermions, what prevents the master is lattice translation. And that's true, that's written in the paper of Kogut and Susskind. So why isn't there a master? Well, that violates lattice translation. Lattice translation by one side. So it's the same physics phrased a little bit different. But the nice thing is it's the same physics that appears in several different places, fits into this language of the renormalization group, together with Luttinger theorem and Haldane's work with the chemical potential and the Heisenberg chain, etc. It's the same physics in all of them, once phrased as an eminent symmetry. And as a bonus, it can also have anomalies.
Thanks.
Okay, awesome. Maybe we can wrap this up. Let's thank.